It is not always possible to solve differential equations algebraically. However, we can learn about the solution through graphical and numerical methods. In the graphical approach, we use direction fields. And this comes from the idea that the derivative is equal to the slope of the equation y at that point. So if my derivative is x minus y, that means the slope of the function y at the point x1, y1, the slope will be x1 minus y1. So, for example, if we were looking at the point 1, 0, then the slope at that point is 1 minus 0, which is 1. So we could draw that out on a graph. Point 1, 0, my slope is 1. We could also look at the point 0, 1, and we'd have the slope is equal to 0 minus 1, which is negative 1. So at the point 0, 1, we have a slope of negative 1. So we can continue making several of these slope lines to get a slope field or a direction field, which will tell us what the graph of the equation y will look like. Here's what a full direction field would look like for our equation. So if we connected these lines, we would have solutions to our differential equations. In other words, we would have our y functions. So all of these are different solutions depending on our constant c when we integrate. Let's consider dy over dt equals y minus 1. So this says that the slope of equation y at any point is equal to y minus 1. So the y coordinate minus 1. So we can create a table of values. So we have our point ty and our slope dy over dt, which is equal to y minus 1. So if we were looking at the point 0, 0, well, the y point is 0. So 0 minus 1 equals negative 1. At 1, 0, we have 0 minus 1, which is negative 1. At 2, 0, we have 0 minus 1, which is negative 1. At 0, 1, our y-coordinate is now 1, so 1 minus 1 is 0. At 1, 1, we have 1 minus 1 is 0. At 2, 1, we have 1 minus 1 is 0. At 0, 2, our y-coordinate is now 2, so 2 minus 1 is 1. At 1, 2, we have 2 minus 1 is 1. And at 2, 2, we have 2 minus 1 is 1. So we can graph these slopes. At 0, 0, we have a slope of negative 1. At 1, 0, we have a slope of negative 1. At 2, 0, we have a slope of negative 1. At 0, 1, we have a slope of 0. At 1, 1, slope of 0. 2, 1, slope of 0. At 0, 2, we have a slope of 1. 1, 2, slope of 1. And 2, 2, a slope of 1. So if we continue with our direction field, we would eventually find that our direction field looks like this. And so here we can get an idea of what our curves look like. And we will find that the general solution is y equals c e to the t plus 1. And we can verify this. Y prime equals c e to the t. And we have y prime equals y minus 1. So y prime equals y minus 1. So c e to the t equals c e to the t plus 1. That's y minus 1. So plus 1 and minus 1 cancel out. So c e to the t equals c e to the t. So that is definitely a solution. And these curves up here are called our family of solutions. This differential equation is a special kind called an autonomous differential equation because f is independent of t. So the derivative here only has y in it. There's no t. So this means that our sign depends on this y minus 1. So we see that when this slope is equal to 0, so 0 equals y minus 1 when y equals 1, which is what we got down here. And then we can determine the sign of the slope on either side by determining if our derivative is positive or negative on either sides of the 0. So if y was 2, we would get a 2 minus 1, which is positive. And if y was 0, we'd have 0 minus 1, which is negative. Looking at the direction field, we can see that above the line y equals 1, all of our solutions have a positive slope. However, below the line y equals 1, all of our solutions have a negative slope. So when dealing with autonomous differential equations, the first step is to determine for what y values our derivative is going to be 0. So in this case, y equals 0, 2, and 5 will give us a slope of 0. And these are said to be equilibrium solutions. And then we use our sign chart to determine in which sections we have positive slope and negative slope. So if y is negative 1, we'll have negative 1 times negative 1 minus 2, 5 minus negative 1. So we have negative times positive, so that's positive. If we were looking at 1, we would have positive 1 times 1 minus 2 is negative. 5 minus 1 is positive, so we'd get a negative. If we were looking at 3, we would have positive. 3 minus 2 is positive, and 5 minus 3 is positive, so we're positive there. And if we were looking at 6, so 6 is positive, 6 minus 2 is positive, 5 minus 6 is negative, so we're negative. So this tells me that our slope for y's less than 0 are positive. So all these have some sort of positive slope. We have 0 slope at 0. We have 0 slope at 2 and 0 slope at 5. We have negative slope between 0 and 2. We have positive slope between 2 and 5. And we have negative slope when y is greater than 5. So this is about what the shape of our graphs of the family of solutions will look like. And when we connect these and determine some of our actual graphs, they'll look something like this. Our numerical approach for approximating differential equations comes from the idea of direction fields. So if we had the differential equation y prime equals x plus 2y, and the initial condition that y of 0 equals 1, then this would tell us that our derivative at the point 0, 1 is 0 plus 2 times 1, which is 2. So drawing that on our graph, we have at the point 0, 1 has a slope of 2. So this line right here, the slope, can approximate the curve at that point. So if we have a linear approximation, that means we're going to use our point slope form. So y minus y1 equals slope times x minus x2. So we have y1 is 1, our slope is 2, and our x, so that should be at x1, our x is 0, So this tells me that y minus 1 equals 2x. So y equals 2x plus 1 is the equation of this line that is approximating our curve. So this line is not a very good approximation for our entire curve. It's really only a good approximation at the point 0, 1. However, we can make this a better approximation if we go over, let's say, 0.5 and create a new linear approximation. So to find our y value when x is 0.5, we're going to use our previous linear approximation. So we have y equals 2 times 0.5 plus 1. So y equals 2. Now that we have our x and y, we can find our slope using our differential equation. So y prime equals x plus 2 times y. So y prime equals 0.5 plus 4, which is 4.5. So that's our new slope. And our equation is y minus y1, which is 2, equals our slope times x minus x1, which is 0.5. So y minus 2 equals 4.5x minus 2.25. So y equals 4.5x minus 0.25. And that's the equation of my new linear approximation. So what I'm doing is I'm connecting a whole bunch of linear approximations. So if we go over 0.5 more to x equals 1, we can find our new linear approximation, our new line segment that's approximating our curve. And if x equals 1, then y equals 4.5 times 1 minus 0.25. So y equals 4.25. So we have the point 1, 4.25. And to find our slope, we're going to use our differential equation. Y prime equals x plus 2 times y. So y prime equals 1 plus 8.5, which is 9.5. So then we have y minus y1, which is 4.25, equals the slope, 9.5, times x minus x1, which is 1. So y minus 4.25 equals 9.5x minus 9.5. So y equals 9.5x minus 5.25. And that's our new linear approximation, our new equation of our line. So we can keep doing the same procedure and get a whole bunch of little lines that will connect to approximate our curve. Here we can see a direction field with one solution in red here, and this purple shows the line segments that you get using Euler's method when we have 4 line segments that create when we have 4 line segments. As we increase our number of line segments, we see that our intervals are shorter and shorter, and they better and better approximate the actual solution to the problem. We can write out the steps for our process called Euler's method. As for y prime of t equals f of ty, so our derivative is a function of t and y, and our initial condition, y of 0 equals a, on some interval 0 to t. Our first step is to choose our change in t. So sometimes this is called a time step. And so or we choose a positive integer n for the number of segments we want to split 0 to t up into. So we get our change in t equals our interval divided by the number of segments. So we have t sub k equals k times delta t for k equals 0, 1, 2, etc. up to n minus 1. So this is which k tells us which segment we're on. So if we are in the first segment, k is 0, so we have tk is equal to 0 times the change in t. So our second step is to let u naught equal y of 0, which is a. Okay, so that's our first y value. So then for k equals 0, 1, 2, up to n minus 1, we find u of k plus 1 equals uk plus f of tk uk delta t. So what this says is that the y value for the next interval is equal to the y value of your current interval plus f of tk, so the x value, comma the y value, so the slope at the point tk uk, times the change times your step length. Okay, so this right here gives you the slope at the point tk uk, because f of ty is y prime of t, and this delta t tells you how long that line goes for, and the uk is the y value at the point tk uk. And each of these u sub k is an approximation to the exact solution y of t sub k.